Hi everyone, welcome to Integral Calculus. Today we explore lesson 9.2, Directional Fields and Euler method. Number 1, intro. Most differential equations are difficult or even impossible to solve in order to obtain an explicit solution. However, we can learn about the solution through two methods. Method 1, directional or slope field, by using slope to sketch the solution curve. Method 2, Euler method, by using tangent lines to approximate the solution. Let's take a look at directional field. Example, let's y prime equal x plus y. Sketch a solution curve that satisfies y2 equal -1. We can sketch a few of them to see. We have the point x, y, and the slope is y prime. Okay, so for 0, 0, slope is 0 plus 0, 0. 0, 1, slope is 1. 1, 2, slope is 3, and so on and so forth. We need to get many points in order to generate the slope field or directional field. And the best way to do this is not by hand, though. We have to use technology. We can go to Google and then we can search for the slope field generator, right? Or slope field plotter. And change the density, make it a little more, and then we can change the length of the vector. See? 0, 0, the slope is flat. So you can see right here, it's flat, right? At the point 0, 1, slope is 1. Yeah, right here. At the point 1, 2, slope is even steeper. That is right. Now we can try to sketch a solution curve that satisfies the given condition y2 equal -1. So for y up 2 equal -1, it gives us the point x equal 2, y equal -1. So at that point 2 and -1 is right here. We're going to follow the flow of the directional field, and the curve would look like this. That's right here. It tells us to go down. So we go down and we're going to follow the flow up. Something like this. Let's get back to the GeoGebra. Here comes the solution. Then go through the point 2, -1. Depending on the initial condition, we may have different solution. Okay. Let's take a look at another example. Example, sketch a solution curve for y prime equal y squared minus y to the 3. For this problem, we can manually do it by hand, because if you look at the differential equation, it is in terms of y. So when y prime is function in terms of y, we call it an autonomous differential equation. And then we can use the phase portrait to sketch. That is, we're going to find the critical number and figure out the increasing, decreasing interval. and then set y prime equal to 0. Y square minus y to the 3 equal to 0. So we have a y square 1 minus y equal to 0. And that gives us y equal to 0, y equal 1. So now we have this is the y-axis right here. Right. We have a horizontal tangent at y equal 0 and y equal 1. Pick some test point. More than 1. Pick 2. Y prime of 2 is less than 0. Meaning that we're going to have a decreasing curve. A decreasing curve would look like this. Pick a number between 0 and 1. Y prime of 1 over 2. And that is more than 0. So it's going to be an increasing curve. Okay. Increasing. Less than 0. Pick -1. Y prime -1 is more than 0. So we're going to have a increasing curve. Increasing. Ta-da! This is the solution curve. Right? 3 of them, depending on the initial condition. Well, let's double check with the GeoGebra. We have a y prime is y square minus y to the 3. Oh, pretty nice. Gonna copy and paste the solution onto the OneNote. Okay. So if we take a look at the slope field or directional field, then we see that, yeah, we have 2 flat tangent line, one at 1 and the other one at 0. And it looks like that the solution curve is going downhill and then it's going to flat out like this. Then from 0 to 1, it is increasing. Look like this. And below 0, it's increasing. Here comes a typical solution curve. Let's take a look at the second method on how to approximate solution. The second method is called Euler method, and Euler method is used to figure out the solution if we have no idea what the solution curve is. So I'm gonna take a look at an unknown solution curve with given condition y of x sub 0 equal y sub 0. So right here we have a point x0 and y0 on the curve. Since we do not know the solution curve, we're gonna use the tangent line because we have a differential equation. The differential equation is gonna give us the slope of the tangent line. So let's take a look at the tangent line through this point. Right here. Okay, so on the tangent line, we're gonna pick another point. X1, Y1. X1, Y1 is not on the solution curve. We can approximate Y sub 1. The way to pick X sub 1 is the difference between X sub 1 and X sub 0. We use this distance as H. H is called the step size. The smaller the value H, the more precise the estimation is going to be. Okay. So now we have a slope at X naught, Y naught is, well, is change in Y over change in X. Slope is the derivative, so that's Y prime X naught, Y naught. Change in Y is Y1 minus Y sub 0. Change in X is the step size H. From here, we see that Y sub 1 is Y sub 0 plus H Y prime X naught, Y naught. Using the step size, we're gonna get X sub 2. So it's also H. Right? And this would be X sub 2. In order to get the point Y sub 2, we're gonna sketch a line tangent to the graph at this point. So look at this line here. It's tangent to the curve. Okay. And here we go. This point, Y sub 2. Using the similar process, then we see that slope at X1, Y1 is the change in Y over change in X. So that would be Y prime X1, Y1. Remember, the point X1, Y1 is not on the solution curve. We get X sub 1 from the step side and Y sub 1 from the equation of the tangent line at the point X0, Y0 and X1, Y1. So here Y prime of X1, Y1 is equal to change in Y. So that would be a Y2 minus Y1 over change in X, H. And then from here we say that, oh, Y2 is, well, Y sub 1 plus H times Y prime of X1, Y1. And then from here we see, oh, that is a recursive formula. So eventually, if we keep going, then Y sub n is Y sub n minus 1 plus H times Y prime of x sub n minus 1, y sub n minus 1. That is the formula that we're going to be using to approximate the solution. Okay, let's take a look at an example. Example, used Euler method with step size 0.1 to approximate values for solution of y prime equal x plus y given y of 0 equal 1. So now we're gonna take a look at what is given to us there. Okay, so we have the step size. That would tell us that h is 0.1. We have the initial condition. It tells us that x sub 0 is equal to 0. Y sub 0 is equal to 1. So from here, we can figure out y sub 1. Y sub 1 is y sub 0 plus h y prime x naught y naught. We just do the substitution. 1 plus 0.1 times 0 plus 1. That gives us the 1.1. Y sub 2 is y sub 1 plus h y prime x1 y1. So that would be a 1.1 plus 0.1 multiply to x sub 1 is 0.1 plus y sub 1 is 1.1. And this gives us 1.22. Y sub 3 is y2 plus h y prime x sub 2 y sub 2, which is 1.22 plus 0.1, and this would be a 0.2 plus 1.22. So that is 1.32. Okay. Well, we can keep going. But what this means is that if yx is the exact solution, then y of 0.1 is approximately y sub 1, which is 1.1. Y of 0.2 is approximately y sub 2, which is 1.22. And y of 0.3 is approximately y sub 3, which is 1.32. That is awesome. Very useful in engineering. Thank you for watching. I hope you found the content useful. Please like and subscribe to help the channel grow. I'll see you in the next video.